All right, so recursion. What is it? Why does it matter? How does it work? And then applications. We'll see that recursion is actually really good for certain kinds of sorting algorithms. Namely, divide and conquer. And if we have time, we'll take a look at recursive binary search. We may not be able to get to it, but merge sort and another algorithm that we haven't looked at and we won't look at today, but quick sort, which is another divide and conquer algorithm. These are both usually implemented recursively if they are. Like merge sort is actually usually taught recursively. We kind of did it imperatively the hard way to give you all some extra reps and sets and to appreciate how awesome recursion is. So, and let me go ahead and just, well, make a file here of code for us to write. I'm just going to do a little bit of talking and using this as a guide, and then we're going to just dive in and write some code. So recursion. Recursion is where a function calls itself. We can actually have functions call themselves, and many of you have probably seen this. It's often used to solve a problem by breaking it down into simpler instances of the same problem, which should sound awfully familiar to divide and conquer algorithms, where we often break a problem down into similar instances of the same problem, right? For divide and conquer. So recursion gets used for all sorts of stuff. As listed here, other applications, it's not just algorithms. It also can be used for traversing trees, for graphs, even for linked lists. So it gets used for all sorts of stuff. When we use recursion, it can improve the time complexity of algorithms. Mainly, it makes our code way easier to read and think about. Sometimes it also does actually improve the time complexity, but for certain algorithms, recursion is just better. It can improve space complexity as well. But again, the real win here is for certain things, recursion is just better. That said, recursion can get really complicated really fast and is not always the best thing. So let's talk about what we're going to do here. And I'm kind of hinting with the code that I'm pulling up here on the left, but this is what we're going to go ahead and write. So if folks are not familiar, the idea of a factorial, and we need a little bit of math to talk about with this to demonstrate, but a factorial, the idea is it's a math thing where you take a number and you multiply it by one less and so on and so on. And like you kind of see here in the curriculum on the right, 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. 2 factorial, 2 times 1. 1 factorial, well, it's just 1. Anyone know what 0 factorial is?
1.
Yeah, exactly. 0 factorial is 1, right? Because, you know, if we continue this pattern and we multiply by 0 at the end, that ruins everything. And this actually becomes important when we talk about recursion. So remember, recursion is subproblems of the same thing. Well, guess what? 5 factorial equals 5 times 4 factorial. 4 factorial equals 4 times 3 factorial. 3 factorial equals 3 times 2 factorial, and so on. And so forth. And so just by looking at this, this is kind of a sign that this is something that recursion is really good for. And you can see the code for it here on the right. And we're going to write it out and we're going to run it. Whenever we're doing recursion, there's always something called a base case. Just like you saw that error that I ran into before, the risk of a function that calls itself. And we can do it, and I'm going to do it right now. This is bad. If I run this code, what's going to happen? Not a trick question, I promise. Let's run it and find out. Oh, Brandon and Daniel.
Yeah, it's gonna be an infinite loop, like what Mikhail said.
Yeah, exactly. I'm not even sure if. Oh, and well, I need to call it. That would help. Yeah, we're gonna get an infinite loop, right? If I just do this, I'm not even sure if Python will let me run this. In fact, we get that same error that you saw that I was running into just a moment ago, recursion error maximum recursion depth exceeded. Because the reality is the way that a computer implements recursion is with a stack, which is a different data structure. We're going to see a little bit in just a minute. A stack is literally like a stack of pancakes. Like you put something on top, and whatever you put on top is the only thing you can grab. And you can only stack like pancakes, or you can only stack plates so high until they topple. So computers can only handle so much. So in order to avoid infinite loops, whenever we're writing a recursive algorithm, we need what's called a base case, which is what tells our algorithm to stop. Right? And let's just maybe write some nice F strings here so we can see what's going on. And for recursion, our base case is if n equals 1 or 0. We return 1. We will stop. We will not recurse. Otherwise, we have a recursive case. Otherwise, what we're going to do is we are going to recurse. But because the goal here is to do a factorial, I want to recurse with n minus 1. In fact, let's just give this an else to make life a little easier to read. I don't think it actually impacts the code. We still need to return code. And what I really want to do is this, right? N times n minus 1, 5 times 4, 5 times 4 times 3, 5 times 4 times 3 times 2 times 1. And there we go. And it might be nice to actually at some point return the value that we compute and print it out. We return it here. Let's capture it. We'll just call this output. And let's just print our output. And let's maybe have this be an F string, and we'll say factorial of, let's do it like this. right? If I got rid of my base case, we'd go on forever. And it wouldn't, we comment that out as well. Right, look how we just kept going. So the base case is the most important aspect of recursion. As you start writing recursive algorithms, it is usually the thing you need to think about first. And then there's the recursive case. And usually what we're doing with recursion is we're calling our same function, but we're modifying its input, right? We're reducing this by 1. 5 times factorial of 4. 4 times factorial of 3, and so on. Let me go ahead and take this, and we're going to put this in Python Tutor, and we're going to visualize it and walk through it. If I can ever remember how to actually get to the Python Tutor code. Here we go. So let's add our factorial function. Let's get rid of the print statement because Python Tutor is going to visualize everything really nicely. Let's get rid of everything but the code so it's easy for us to look at. And I think that's a good start. And let's hit visualize execution and watch what happens. And let me make this a bit bigger so we don't have to look at the ads. So we're about to see the call stack in action. And the call stack is literally, you can think of it as an array. But when I call a function, Python under the hood, the computer under the hood, not just the programming language, but the operating system, throws it on the call stack. And every time I call a function, it gets added to that call stack. And it gets added to the top. And so on and so forth. And so my code is going to keep doing this, right? Because this is what I've written my code to do. If we look at this code, when I call factorial 5, we don't hit this base case. I return, I multiply, but before I can finish this, I call the function again. So what does the computer do? It puts the new function call on the top of the call stack. And then at this point, we hit our base case, we're done. It returns something, the top of the stack gets removed. That returns something, that gets removed. So on and so forth. And that's what we're about to see visualized much better and comprehensively here in Python Tutor. I can get rid of all these other Python tutors. So let's watch this in action. That's our base case. Obviously, we're starting at 5, so we're not there. We call our function again, right? We return, but I can't return because I have to call this function again before I can return. The 4 just got added, right? It's been added to the call stack. In this visualization, the call stack is growing down, but 4 is now on top of the call stack. Our function is called again, factorial, where n equals 4. No base case. Hey, I need to call factorial again for n equals 3. right? I can't compute that return statement until I've done all this work. N equals 2. N equals 1. Now what's going to happen when I hit next? Someone want to tell me? Daniel, yes, sir.
It's gonna now multiply all those stacks together.
Yeah, exactly. We're about to finally return 1. We're finally going to return an actual value. This is a very exciting moment. See that return value right there for factorial n of 2? We called that function, but we couldn't compute its return value. Now we finally have a return value. Same now with factorial of 3. We can actually figure out that return value, 3 times 2. And so this part right here, right now we're finally returning stuff. And let me undo the thing. Right, 6 times 4, 24. Right, 5 times 24 is what? Anyone?
120?
Yeah. The way I do it is 5 times 20 is 100 and 5 times 4 is 20, and I add them together. And that's our factorial value, right? Of 5 factorial. So this is the basic concept of recursion. And you can see how for computing a factorial, writing the algorithm recursively is way better than doing it imperatively, doing it the other way. Let me just check in and see what questions people have and how people are feeling. Good, bad, indifferent? What do we think? Murad, yes, sir.
I just want to make some up, but by mistake. Sorry.
Oh, no worries. Do we want to see like another example of another recursive algorithm here in Python Tutor to kind of see it in action?
Sure.
Okay. Yeah, let's take a look. And the call stack is an important idea too. And to be clear, like Python has a call stack, but like the computer has a call stack too. And this is how computers keep track of stuff. Let's make an even simpler recursive function, and then we'll look at a couple more interesting ones. Let's just make a countdown function. And what I want to do actually is count down from n to 0. And so I want to print n, but I want to do it recursively. And maybe can you guys help me like write this algorithm? So like our goal here is if num is 5 and we do, count down 5. What I want to see, what I want to see is I want to see printed out 5, 4, 3, 2, 1. And yeah, I want to see 0. So I want those 5 print statements, but I want my algorithm to be recursive. Can someone tell me what code I need to add here? Because right now, if I run it, it's just gonna print 5, right? Daniel, yes, sir.
You need to put a base case to prevent it going into an infinite loop.
Yeah, absolutely. Walk me through adding a base case.
Yeah, so you can say if n is equal to 0 or 1, return n.
Okay. Why 0 or 1?
Oh, we probably just return just 0.
Yeah, we can just return. Yeah, I think we can just return n. We can see if we need to add it. The reason I did both for the factorial, by the way, was if we did say factorial 0, the base case needs to handle that, right? And if n was just 1, for the factorial algorithm, that wouldn't work. But here for countdown, it's less of an issue. If n is 0, return n. I love it. And now I need, Daniel, you want to help me out maybe and add the recursive case as well?
Yeah, I can try. So now we can say else. We can say else return n minus 1 question mark.
I like it. Where do I call the function inside itself? Chris, yes, sir.
Would you, in the return statement, would you say countdown underscore, count underscore down and then parentheses n minus 1?
Yeah, exactly. And Daniel, I think that's kind of what you were thinking as well. And this is, again, really common with the recursive case, where the recursive case, we need this return statement because once this has done all its work and it gets to our base case, right? Once we hit 0, I want, return 0. I want 0 returned here. You know how we sort of saw things rolled back up in Python Tutor? But then also when we recurse, we often need to like decrement our counter or something like that. Okay, before we run this code, what do we think the output will be for count 0? If I run count 0, what will this function output? And what will it print? Murad, yes, sir.
0. You put
Yeah, it'll return 0.
base case here.
Will it print 0? Daniel, yes, sir.
I don't think it'll print in 0. It's because since the base case is 0, it'll just return the first call stack, which is 1.
Yeah. Exactly. I mean, it's not even going to get to 1 for 0, right? If we run this code, countdown of 0, n equals 0 is true, we return 0, we're done, right? What about count of 1? So what happens with count of 1? Do we go inside our if statement? Daniel, yes, sir.
If it's count of 1, does it go? It starts returning the call stack then.
Yeah. Count of 1. N is not 0, right? So we go to the else. So we go to return, and then we call count 0. Right? And then we have count of 0, and then we return 0. Do we ever get to this print statement? Chris, yes, sir.
No. Oh,
Correct.
don't.
We do
No,
not.
okay.
Where can I put the print statement? So every time it prints out n for count of 0, count of 1, count of anything.
Would it be inside the if statement and inside of else? Or just the if statement?
Close. So if I put it inside the else, will it print for if I call count of 0? Do we ever get to that else statement?
No, no.
Correct. Right? It'll print for everything but 0, which is a common challenge with recursive algorithms, that edge case of the base case. And if I put it inside here, it only prints for 0. Where can I put it where it'll print for both of them? Where it'll print both for my base case and my recursive case? And the answer is a lot simpler than people think it is. I can put it right there at the top.
Oh, true.
Mikhail, yes, sir. Yeah.
No, I was gonna say.
Yeah, sorry, I didn't mean to steal your thunder. So when I learned computer science, like this is how we learned all this stuff. They made us like do it on a whiteboard and talk through it. And it's actually really, really good because this is how you learn to like mentally model what the program is doing. Right. But you can see how like when you're not used to it, even for something like this, there's a lot of things to think through and a lot of steps. And so that's why I just wanted to walk through this a little bit, but now let's use Python Tutor. Let's visualize it. This will be a lot more fun. But now that we've thought through that really simple example, and look how much value we got out of, count 0, count 1. Those are not complicated things for us to think through. And look how great that was in helping us design our algorithm, right? We were asking about lead code questions. This is how you tackle those as well. Come up with a dirt simple example and literally walk through it line by line on a piece of paper, sort of in your head. We recurse, right? We're about to call countdown and pass it 4. And we see 5 got printed right off the bat, which is great. We're calling countdown for 4. It's been added to the call stack. Remember in this visualization with Python Tutor, the call stack is growing down. So countdown of 4 is actually at the top of our call stack. We recurse again, right? Countdown of 3. Note how nothing has returned, right? None of these function calls have returned anything. And that's what the call stack is for, to keep track of stuff. Because if it's on the top, then it's what the computer has to handle. If I scroll down, there's countdown of 1. We've seen 5, 4, 3, 2 printed out. 1 gets printed. We're not at 0. We recurse one more time. We print that 0. We're about to hit our base case. Exciting moment. And in fact, all the way down there, we see count of 0 has been added at the bottom of the call stack. And now we start rolling it back up, right? Each of these function calls is now returning. The computer takes it off the call stack because it returns something. And so now over here, right, I've got return countdown of 1 is 0, so we can return 0. In fact, the return value for all this stuff is 0. It actually is not that interesting now that I think about it, because we don't add anything together like we did with the factorial. So this is actually a good thing to point out. Like for some recursive algorithms, what we care about is what we return. For this one, what we actually care about is what we print, right? The return statement actually doesn't really matter here because we're always going to return 0. Do you guys see why that is? That why no matter what I put in for countdown, like we're just returning 0 all day, every day? Right? Because I don't return anything till I get here. I finally return n. What is n going to be at line 6 in this code 100% of the time? Yeah, exactly. Yeah, Mickey, I love it. Right? And here, what do I return? Whatever the heck the recursive function call returned. So count of 0 returns 0, which is what count of 1 returns and count of 2 returns and so on. And, you know, I didn't mean to make the smiley face, but now it's there. So this just returns 0. But the print is the interesting part, right? And that was what we actually had to think through. And now we can watch this wrap back up. So that's recursion. I have to wrap in a couple minutes to go to my meeting. But we've covered the main things that we want to cover. I'm going to show us binary search recursively, and that'll be a good stopping point. This lesson has some good material. It also walks through the Fibonacci sequence, which is another classic example of recursion, where we add up 2 numbers to get the next. We've visualized the call stack in Python Tutor. If you want a challenge, and I highly recommend this, write a factorial function that goes up instead of down. And in fact, the implementation is here, where I give it a factorial, but the way it builds itself up is actually by incrementing. I also have a classic programming problem, a recursive programming problem called the Towers of Hanoi. That's sort of a weekend project that I will release the GitHub for a little later in the day. It's a great problem. Let me give you all just a quick preview of it. It's a little different than the ones that we've done. Oh, I'm in the wrong spot. I will find it and share it later, along with sort of a description. But it is essentially like you'll want to think on it the whole weekend, and you'll end up writing like 4 lines of code. Before we wrap, I just want to show us binary search recursively in Python. And then I apologize, but I do have to go. And the good news is that binary search in Python, or binary search recursively, is a lot of fun. Binary search and merge sort are sort of the classic examples. And I think I'm just going to paste this in the interest of time so we can talk about it. Because if you think about divide and conquer, right? If we go back to talking about sorting algorithms and we look at merge sort and we look at that crazy diagram, if you look at this now, this looks an awful lot like recursion, right? And that's what you'll see how to do, how to implement merge sort recursively. Binary search, implemented recursively is a lot of fun and a lot cleaner, right? Where we're searching through, we're dividing and conquering, but we just call the function on itself to search the smaller set. So I apologize, folks. I do have to switch gears. Let me go ahead and stop the recording.